concept of convolution. And like I was saying, convolution is a fundamental law in nature. So if we feed any input to the system, if we know the impulse response, then the output is always related to the input via the convolution of the impulse response, right? And what does convolution mean in terms of real calculations? It's this integral as we saw over here. To understand it intuitively, what is it doing? As you saw, t minus tau basically means first do minus tau, which basically flips the signal, then t added basically starts to slide it. So as we slide it, we multiply and integrate, and whatever answer that produces is the answer of the convolution. So as you can see, essentially if we gave it two signals, and if we did the convolution, it will produce the highest peak wherever there was the maximum overlap between the two signals, right? So this was for continuous time signals. Very similarly, if we have discrete time signals, let's say we are sampling something, let's say this is 1, this is 2. Okay, so let's call this x of n. So this is the n. Okay, and let's say we have some h over here. Let's say this is 4, this is 5, right? So at 4 and 5, it produces a value of 1. Okay, so again, the way the convolution will be defined will be y of n equal to x of n convolution h of n, right? So instead of the integral now, this will be a summation. So x of n minus k, h of k equal to minus infinity to infinity. So this is how the y of n will look like. Okay, so again, it's very easy to compute. Okay, so again, we are switching to the k scale, then we are doing minus k. N is basically the sliding of this. For example, as I switch it to the k scale and do a minus k, this is how x of minus k will look like, right? For example, what will x of 1 minus k look like? So if n is 1, okay, that means this got slided to the right. So this is how it will be. Okay, or let's take a look at x of 2 minus k. So then basically this will appear at 2, correct? So we flipped, then 1, then 2. So this is how the x of 2 minus k will look like, right? Okay, so very similarly, as you can see, when will it produce the overlap? At x of 4 minus k, correct? Because at that time, okay, so at that time, as I flipped and start sliding it, this will be basically like this. 1 times 1 is 1, because this basically means summation, right? So this will be basically, so as far as the y of n is concerned, it will have a value of 1 at 4. Okay, then as we go to 5, so as we put n equal to 5, you can see then the blues are over here, right? So pretend this is our blue signal over here. So this will be at 4 and 5. So now it will be 1 times 1 plus 1 times 1, which is 2. So we'll produce an output of 2. Correct? Then what will happen as n moves to 6? It will decrease back to 1 and then go back to 0. right? So this is how the convolution of two discrete signals will look like in the discrete domain, right? Okay, now often when we deal with images are two-dimensional. Okay, so very similarly, we can have a convolution in 2 dimensions. So okay, so convolution in 2D might look something like this. Okay, let's say y of ij. There will be 2 summations involved. Okay. K1 equal to negative infinity to infinity. K2 equal to negative infinity to infinity. Then x of I minus K1, J minus K1. And multiply with h of K1, K2. Okay, so this is how the 2D convolution would look like. In the same way, we can have, if there were 3 dimensions involved, 4 dimensions involved, we can have convolution in the 3 dimensions, 4 dimensions, and so on, right? Okay, so just like the key idea once again was flip it, right? Flip it, slide it, multiply, and accumulate. So if we have images over here, so let me show you in terms of images, what does convolution mean? Okay, so let's say we have a grayscale image, right? Suppose these are the pixel values, 80, 90, 50, 40, 30, and so on. Okay, 60, 20, 10, right, 90, 40, and so on. Okay, 20, 10, 30, 50, 20, and so on. And let me put one more. 60, 40, 20, 10, and so on. So let's pretend these are the grayscale pixel values. Okay. So pretend this is our image I. Okay. And now we want to do a convolution with let's say 1, 0, 0, 0, 1, 1, minus 1, 0, something like this. Okay. Suppose we call this K. Okay, K is what we call our kernel. So K is referred to as kernel. So when we do convolution of two-dimensional data, their size does not have to be the same. One could be bigger, one could be smaller. Okay. So once again, just like we were flipping, sliding, multiplying, and accumulating, exact same thing we'll do in the 2 dimensions. Okay. Now it was very easy to see in 1 dimension how the flip works. So for example, okay, if I'm given a signal, let's say 1, 2, 1, and let's say 3. So 1, 2, 1, 3. Okay, so if I flip it, right, like to do something minus k on the k scale, then what will happen? This will become 1. Right? This 2 will move to the negative 1, then 1, and then, see, this was 1, 2, 3. So at negative 3, you'll see it will be 3, right? So it's easy flipping is easy to do in 1 dimension, but the question is, if we have a 2-dimensional data, then how do we flip before we start sliding and multiplying and accumulating it, right? Okay, and those of you who are in the computer vision are very fluent with it. So basically what we do is in 2D, we need to rotate by 180 degrees. Okay, easy way to accomplish this is do 2 90-degree rotations. Okay, so let me show you after we rotate this by 90 degrees. So after 90-degree rotation, what will happen to this one? Okay, this 100 will move over here. So the top row becomes the top column, right? Then this 010 basically moves over here. 010. It was on the right, now it became at the bottom. Then this 0 minus 1, 1 goes over here, and lastly 101. So this is what will happen after we rotate it by 90 degrees. Then if we further rotate it by 90 degrees, okay, move this 101 on the right. Okay, then 100, right? Then 010, and lastly 0 minus 11. So that will be the answer after rotating by 180 degrees.
Choose 2 transpose.
Oops, in the middle is 1.
Which is basically 2 transpose.
In a 3 by 3 it is, but if we go higher, it's not a transpose anymore. So anyway, so once we have the rotated kernel, then like I said, we'll start sliding and multiplying and adding. So if I did, for example, this kernel over here, after it has been rotated, so I'll put it in a different color, 0, minus 1, 1, 1, 1, 0, and 0, 0, 1. Okay, so basically the kernel is now in the first spot. Okay, so our answer that it will produce will be, as you can see, 80 times 0 plus 90 times minus 1 plus 50 times 1 plus 60 times 1 plus 20 times 1 plus 10 times 0 plus 20 times 0 plus 10 times 0 plus 30 times 1. So what is this number equal to? Minus 90 plus 50 will give me minus 40 in the first row, then 60 and 20, 80 in the second row, and 30 in the last row. So 110 minus 40, 70, right? So this was the answer when the kernel was placed in the first 3 by 3 spot. So the answer that it will produce will be, the first output will be 70, right in this spot. Okay? Or you can also put it in the center over here. This is the center pixel. So wherever this 20 pixel is, right at this spot, we will put 70. We will not put anything in the first row. We will not put anything in the first column. Right? Okay, so that's how the first convolution answer is produced. Now we move the kernel 1 pixel to the right. So if I move the kernel 1 pixel to the right, okay, and then you'll get the idea. I will repeat that after that. So now let's move this kernel in this spot. Okay, so again the kernel is 0, minus 1, 1, 1, 1, 0, and 0, 0, 1. Okay, so we can easily multiply now. 90 is being multiplied. This is minus 50 plus 40 will be minus 10 in the first row. Then 20 plus 10, 30 in the second row. And lastly, 50 in the last row. So what's that? 70 again? Okay, so in the next part, it will be 70 again. Right? Same way we move it to, so as you can see, each time we move the kernel, we'll compute one value. Whatever the multiplication in sum is, so this is the answer of the convolution over here. Because whatever the center point is, that's where we place this value. Okay, as you can see, the first row, first column, last row, last column are invalid. So no data is produced over here. So that's how the convolution works in the two-dimensional space when images are involved. So once again, you'll be given some kind of a kernel. Okay, you'll rotate it 180 degrees, and then you'll start sliding. You reach all the way to the end of the row. Then you start moving one pixel down. So then you start moving in the next row, next row. So you'll keep producing some answer. But nothing in the first row or the last row or the first column or the last column, right? Okay, so that's the idea of a convolution. Now the next related question is, why are we doing this? Okay, what benefit does it give us? Okay, so depending on the kernel, okay, we enhance the image. In a certain way. Okay, so let me develop a little bit of the intuitive ideas over here. Then, as we take a look at the deep network, it will make a lot more sense why we are doing this, right? Okay, so let's sidetrack a little bit. Okay, forget the two-dimensional kernels and the two-dimensional convolution. Okay. So let's talk about removing high frequencies from data. Okay, so the data could be like a speech signal, or the data could be even a financial data, like a price of a stock, right? So for example, if you take a look at, let's say, price of IBM stock, what you will see is every day it moves up and down. Sometimes it will move up or down for a week. So this is how it may behave over a period of time, right? So people who are in the financial world don't worry about day-to-day changes. They wanted to see over a long term, what is the trend? Is it going upwards, or is it going? So a common technique that we use is called the moving average filter. So for example, we can say, okay, go to the last, for example, 5 days, and take the average of those. So if we went over here, went over here, went over here, went over, so we added these 5 data points. Whatever the average is, we replaced it by the average value. So as you can see, our first data point may be somewhere over here. So same way, we move the window 1 day to the right. So the next 5 days, so this was first 5 days, then next 5 days. So we keep moving it 1 day, right? So if we replaced it by the average, you'll see it will be a lot smoother curve. Okay, so now it's easy to see is the trend downwards rather than daily up and down changes. So a simple averaging, basically, so simple averaging acts as what we call a low-pass filter. Meaning, it blocks high frequencies. A frequency is like a change. So if there's a sudden change, there's a high frequency. So all of these things, up and down, those are high frequencies. So as you guys saw, if we simply took the moving average and plotted it, it will be a lot smoother curve, right? Okay, so very similarly, coming to our images over here. Again, if we took a picture of, let's say, a tree or a table or something, anytime there's a edge involved, you will see it produces high frequencies. Okay, so sometimes on purpose we want to blur it so that it gradually blends in with the background over here. So one easy way to do that would be create a kernel which does the averaging. Okay, so how can we create a kernel that will do the averaging? What will be the values? So in this case, what we want to do is take the average of the 9 values. Okay, so take a look over here. What if we did this? Make the kernel all ones divided by 9. Okay, so what will it do? If the kernel is in the first spot, 80 plus 90 plus 40 plus 60 plus 20 plus 10 plus 20 plus 10 plus 30 divided by? Isn't that the average? So same way we move this. So what we'll do is we'll end up getting a lot, sort of like a blurry picture where the edges will be, the effect of the edges will be not as sharp. Okay? And like I said, sometimes on purpose we want that. So if that was the goal, to remove the high frequencies, you can come up with the kernel, right? Same way, those of you in computer vision, we have studied many kernels. For example, some of you would recall from computer vision. If the kernel is, let's say, -1, -2, -1, 0, 0, 0, 1, 2, 1.
Enhance the edges.
Okay, this will enhance the horizontal edges. Okay, same way if I put it on this, it will enhance the vertical edges. So we have different kinds of kernels that we can design. Those of you in computer vision, if you recall, for example, we did Laplacian filters, which were based on the second derivative. We computed the Taylor series. Based on the Taylor series, we came up with the kernel, right? Okay, so one approach is we design the kernel. So think of it this way. From a deep learning point of view, okay, one approach would be, okay, here's our input image. So let me call it X. Okay, we do some kind of a pre-processing. Okay, for example, applying kernels. Or applying a single kernel. Let's think about it, right? So, let's say this kernel was enhancing the edges. Okay, let's say our neural network was designed to detect whether it's a table or not. Okay, with the table, right, edges are important. So if we pre-processed it, what we will find is it does a lot better job in recognition whether it's a table or not, as opposed to not doing any pre-processing and feeding it directly to the neural network. So that's the idea behind deep convolutional networks, is do some kind of a pre-processing. Again, use neural networks to do the pre-processing, okay? And they will be doing the convolutions, and that's why we call it deep CNN. So our next topic is deep CNN. So today, let me give you the architecture of a deep CNN. Next lecture, I'll go over in detail the backpropagation, which is very complicated for a deep CNN. And then, like I said, one time you have to write the code for a CNN by yourself, okay? Not use any library, meaning the TensorFlow. So let's take a look at the architecture of a CNN and at least develop the intuition today and the details next time. Okay, so like I was saying, the fundamental concept is have some pre-processing done, so we'll feed in some image or other data, doesn't have to be an image. Okay, could be text data, could be speech data, so it could be any kind of data. So we'll do some pre-processing in terms of convolutions. Okay, and then we'll feed it to a classifier. Okay, which in our case will be a dense network. And then we will do the classification. So let me ask you a simple question. Let's pretend somehow we came up with these convolutions. Okay, it doesn't matter there's a single layer of these or 10 layers of these. Let's pretend it's doing some enhancement on the image, right? After it's done enhancing, now we want to know what type of object it is. So if you're creating this dense network, how many layers will you pick over here? One hidden layer, right?
Yeah.
Because it doesn't, will it help you if you made it like 2 hidden layers?
No, according to the universal.
No, it doesn't. So the last stage of our deep CNN you will see is extremely easy. It's just a regular neural network, which you already know how to design, how to do the backpropagation on it. So this is a piece of cake. Okay, so the difficulty in a CNN is how do we do these convolutions? Okay, and let me show you, it's not too complicated either, but programming it, understanding the backpropagation is complicated. Okay, so this is what we'll do. So that we can easily relate to our digit recognition, let me draw the architecture of a deep CNN for doing digit recognition and see if you guys agree that it is making sense. Okay, so suppose we take a look at 28 by 28 image. Okay, unlike previously where we were converting it into a 784 by 1 and then feeding it to a neural network, there's no need for it. We will leave it as a 2-dimensional matrix. In fact, later on, once we put color channels over here, we'll convert it to a tensor where this will be a 3-dimensional matrix. Okay, so no need for this. Okay, so now what we'll do is we'll apply, let's say, 1 kernel. So this is basically doing a convolution. Okay, so before I go further, let me ask you this. If I gave you a 28 by 28 matrix, if I gave you a 3 by 3 kernel, okay, Does it produce an answer in the very top left corner?
It will be blank.
It will be, the top row is blank or not known, right? The entire answer is inside, meaning from the second row, second column will be the first answer that will produce, right? So what will be the size after convolution? So don't count the data that we don't know.
26 by 26.
So it will be, so if we did a convolution over here, this will be 26 by 26. Okay, what if I make this convolution filter 5 by 5?
Still 26 by 26.
No. See, if this is, let's say, a 5 by 5.
24, 24?
Correct.
There's a formula for it.
See, the first output it will produce, as you will see, will be in the center over here, right? So the top two rows, top two columns will now not be having any valid data. So now two rows are eliminated, two columns are eliminated. So as you can see now this will be 24 by 24. So in general, basically if the size is n by n, and this is, let's say, k by k as an example, so after the convolution it will be n minus k plus 1. So 28 minus 5, 23 plus 1, 24 by 24 will be the size of the convolution, right?
And we have to use odd number kernel. We can't use even number. Like we can't use 6 by 6 kernel.
Yeah, we always use odd number because then we have a center where we can see. Theoretically, you can use an even number, okay, but in practice we use odd numbers. Okay. Okay, anyway, so let's go over here. So we apply, let's say, a 5 by 5 convolution. So what answer will it produce?
4 by 20.
No, it's 5 by 5. 24 by 24, right? So this will produce 24 by 24. Everybody agrees? Now what we do is to every element we add a bias. Let me call it B1. Because we'll have, so let's say the first number is 0.89. And by the way, we'll scale it with 255 before we feed it to the convolutions. Okay, so anyway, whatever that number is, we'll keep adding the bias to it. So the entire convolution will have a single bias. Okay. As we do this, then we'll pass it through an activation function. Okay, which could be a sigmoid, which could be whatever. So that's the answer of our. So whatever we get, we call this a feature map. So in the technical terminology, we apply a convolution, we add a bias, we pass it through an activation function, and then whatever we get is called the feature map. Okay, so in a CNN, rather than just applying a single 5 by 5 convolution, we do many in parallel. Okay, so suppose we decide to do 6 convolutions.